Okay, so next week, supposedly Wednesday, we will be taking our quiz on the algebra review packet, that yellow packet, and the answers are posted, solutions are posted online. Go into updates, and you'll see the updates there. The answer to the derivative packet, integral packet, is also there, so you can go ahead and check your answers. And if you get stuck on the algebra stuff, and supposedly we're doing it Wednesday, I'm skeptical. I don't think it's going to happen. It was a yellow packet. It was over there too, but I gave it to you a while ago. But you can look for it. Also, all the handouts should be online. I got to make sure. I'm not sure I got everything up there, but I worked on that yesterday. Okay, for slope fields, what we're going to do is we have a differential equation here. Do you remember what a differential equation is? It's an equation which involves derivatives whose solution is a function. So I'm going to look at this differential equation, and first let's solve it. Let's see if we can solve it correctly. I will multiply by dx, so dy is equal to cosine of x dx. And everything's fine because I have all the x's on one side and the y's on the other. You'll see on the worksheet that's not always going to happen. Okay, so what do we do next? We integrate, right? So we're going to integrate that. What's the left side? What's the antiderivative of 1 dy? It's just y. Now, what's the antiderivative of the cosine? Let's check it. I did that in the last class, and is that right? Is the derivative of the negative sign a positive cosine? No, the derivative of the cofunctions is always negative. So this is not correct. The derivative of the sine function is cosine. I always check. The derivative of sine function is positive. The derivative of cosine is negative. Okay. Check it. Take the derivative of the sine, you'll get positive cosine. Yeah, and I didn't catch it in the last class, but that's okay. We fixed it because when we did the slope field, I realized I made a mistake. We're going to do the slope field. Okay, that is the solution to this differential equation. We know what that looks like. You know what a sine curve looks like. But what happens is sometimes we get differential equations, you cannot solve them algebraically. And within our class, there are some that can be solved algebraically, but we'll never learn that this year. It's beyond this course. There's a whole course called differential equations, and we call it diff-EQ. Everybody calls it diff-EQ. And so that's when you'll learn about some techniques of solving differential equations. So what we're going to do is learn a technique to look at the solutions, what the solution curve might look like, I suppose. So I want to look at the solution curve, what this might look like. We're going to do it graphically. And so what we're going to do is take different points in the plane here, and I'm going to make this one pi over 2, and I'm going to make this one pi, because we're doing cosine. Normally we're doing numbers. Make this one minus pi over 2, and this one minus pi. And then the y-axis will count up by ones. And what I'm going to do at each point in the plane that I choose, I'm going to calculate the slope of the tangent line to the original curve. We know what it is. We know it's the sine function. So I'm going to make a table of values, and eventually I probably won't use them all. So at the origin, 0, 0, what is the slope at the origin? Remember, the y dx is the slope. It's the cosine of 0. Now, I better draw a cosine curve so we get this right. Is it 0? Is the cosine of 0, 0? No, it's 1. So that the slope at the origin is the cosine of 0, which is 1. And what I'm going to draw on my graph is just a little piece of the tangent line. This is actually how your graphs are created, but they're much tinier. They're so small, those little pixels, you can't see them, and it looks continuous when you look at your cosine curve on your graphing calculator. And you'll need to get the programs from me, because there is a slope field program on there. It's really cool, so you can look at these. So this is I'm going to draw a tangent line that's a little too big. Just a little piece of a tangent line. And I'm going to do this for all the points in the ordered plane, in the coordinate plane. And you're saying, well, I don't want to do that. There's too many points. On the exam, you only have to do about 9 points. And they will not look at it for a table of values. You can or can't. It's up to you. They will only look at your answer. Well, I'm going to let x continue to be 0 and make y equal to 1. So at this point right here, what is the slope at 0, 1? Does this depend on y? There's still 1. No, there's no y in there, which is kind of nice. So the slope is still 1. Let's take the next point. When x is 0 and y is 2, it's still the cosine of 0. What's the slope there? I'm just evaluating my slope at x equals 0. It's independent of the y. There's no y there. If there had been 2 y cosine x, it'd be a way different picture. It's still going to be 1. What's going to be true about all the slopes on the y-axis? They're all going to be 1. I like it when there's only one variable in my slope. It can be 2, unfortunately. And where do these derivatives come from? They come from the implicit differentiation. If you remember when we did that a long time ago. We'll hit on that again next week. Because I'm just graphing a little tiny piece of the tangent line. The tangent line would look like this. Yes, I'm just looking at the slope of the tangent line at that ordered pair. Okay, let's do pi over 2. When x is pi over 2, and let's get back on the x-axis, and y is 0, then we're going to do the cosine of pi over 2. And what's the cosine of pi over 2? I'll draw my picture. Because this is pi, this is, sorry, that's 2 pi. And this is pi, and there's pi over 2. Right, it's 0. So now this little graph makes it so much easier, I just draw it. And the day of the exam, when you get in there, just draw your cosine and your sine graph, maybe your tangent graph, and then you can refer back to it when you need to. It doesn't help, like for the cosine of 45 degrees, but it does for the ones on the axes, called the quadrantal angles. And this is 0. So at pi over 2, when I'm on the x-axis, the slope of the tangent line will be 0. I'm just looking at the tangent lines. They're going to have to look somewhat like the curve. Now, have we come to the conclusion that no matter where I am on the y's, it's always going to be 0? Okay, so these are always 0. And all of a sudden, it's going to pop out at you when I get enough points here. Okay, what about at pi? What's the cosine of pi? Well, it's -1. So the slope at pi is going to be -1. What'd you say?
Lost pi.
That's on Pi Day. It's coming.
Oh, yes it is.
Now, especially as I stand back, I start to see something. Let's do -pi over 2. What is the slope? That's -1. What about -pi over 2? What's the slope here? Well, there's -pi over 2. What's the slope there? 0. So this is 0. Whoopsie. Oh, I didn't want to erase all that, but that's okay. And this is 0. And now what I'm going to do is pick up a point. It doesn't matter what point. Actually, I'm going to use the thicker marker. I'm going to start here, and these little tangent lines point me in the direction that the curve is going. Remember, you could do you'd fill up the whole plane, but you could do it at every single point. So it's pointing me this way, and then I can see it's going to zero out, and it's going to come down here, and this is going to be coming down here, and it's going to zero out. What graph is this? That's the sine graph. Well, we knew that because we could solve for that. Remember? Not everything can be solved. And so all this is, it gives you a snapshot of what could be, or is a picture of the solution curve. And what does the C do? All the C does, oh, it's not joined, is shifts this up. That's all it does. Now can I do this? Yeah, that's all the C does. It makes it go up and down. Isn't the slope the same everywhere? That's amazing that I did that freehand, almost exactly the same. Seriously. I Can't believe it. I've been doing this too long, haven't I? Okay, so that's all the C does. That's why you always add the C, because you don't know where it is in the plane this function is. Okay, so let's try some off your worksheet. So you still have to flip it over. I have to bring it up. Do I have it here? No. And the answer should be up on Schoology, but I'll make sure that they're there. Okay. And, it's up to you if you want to do a table of values or not. We'll do these two problems. This next one comes out, number 3 comes out really strange looking because it has both an X and Y in it. That one you're going to need a table of values. If you have my programs, the slope field program, then you can actually take a look at what they might look like. Kind of cool. There's other ways to look at solutions to differential equations. They're called, there's Euler's method, which is actually creating values of where the next point should be or close to where it would be. It's approximation. So there's a lot of different things that we can do with differential equations, but most of them cannot be solved. And the problem is when you collect data, you're collecting data of the derivative, never of the function. It's always rates. What's the population growth? That sort of thing. It's always a rate. And you can probably give me more examples from your science class. So we'll make a little table of values to start. X, Y, and my slope is X plus 1. Oh, I always like to start at the origin. I like the easy thing. So what's the slope at the origin? 1. So I'll draw a little piece of a tangent line there. That's all it is. Pieces of tangent lines. So that I can look. We can solve this one, and you'll see why it looks like what it looks like. Okay, so if X is equal to 0 and Y is equal to 1, my slope is still, X is 0, 0 plus 1 is still 1. These are going to be the same vertically, aren't they? If X is equal to 0 and Y is 2, what's the slope? No, it's 0 plus 1. It's 1. So what's going to be true on the y-axis? They're all going to be 1. Okay, we've got to try another x value, because x is the only thing that's changing my slope. What would you like to try? -1. Is there a reason you chose -1? What's the slope at -1? 0. So at -1, this is going to be 0. They're all going to be the same vertically. That one's going to be different, because it has y's in it, not x's. Okay, what about x equal to 1? 1 gives me a slope of 2. Sorry, I just don't have any room. So it's getting steeper. So see, I don't have to do a table of values for every single one. I'm hoping that my slope is only a function of x or only a function of y. And when you you work the slope field program, you actually type in the y from the keyboard. Okay, and what about at 2? It's what? That's 3. So it's getting really steep. Let's go the other direction. What if x is equal to -2? Then the slope is -1. I like it when there's only one variable there, because then it's easy. And then this is what? -2. You've seen direction fields. They have them on the weather. Did you ever play with magnets when you were younger? You looked at the metal filings? That's a direction field. They even call it that, don't they? In science class? Yeah, that's all it is. So it's just like that. This gives me the direction of my function. So if I pick this point, it's flat here, but as I go over here, the slope's increasing, it's getting pretty steep. What does this look like? It looks like a parabola. Are we surprised? What's the antiderivative of x plus 1? It's x squared over 2 plus x plus some constant. And that's just the vertical shift. It's kind of cool. So you shouldn't find this terribly difficult. It's all going to be drawing type of things. This one's a little different. If we try to solve that one, by separating the variables, we get dy equals 2y dx. I got a problem right now, and this is when things are going to get harder, is when we have variables like this. This says I can only have x's over here. That's why the differential is critical. So I don't want the y there. How can I get rid of it? Divide. And then I'm going to rewrite this as 1 over y dy equals dx. And if we anti-differentiate the left side, does anybody know what I get? No? How about if I wrote it this way? 1 over x dx. That's that one. That's the natural log. Oh, I forgot the 2. Whoops. It'll just be a factor. It's not a big deal. So this is the log of y would be equal to 2x plus some constant. And then we don't like to solve for that. But that's the nature of what it's going to be like on the exam. It's going to be a log. And I don't want the log of y. I want what y is. What kind of function is this going to be? Well, let's do the slope field and see. Okay, so when x, I think I have room here, x, y, slope. When x is 0 and y is 0, what's the slope? 0. So I have a 0 slope right there. Let's let the x's increase. When x is 1 and y is 0, what's the slope? 0. When x is 2 and y is 0, the slope is 0. When they're all the same horizontally, it's called a homogeneous differential equation. I like those because I don't have to do so much work. You see why they're all going to be the same horizontally? They were all the same vertically with the x's. But the y's will all be the same horizontally. What about at 1? The slope is going to be 2. It gets pretty steep. I wanted to make it vertical, but that would be wrong. And when I go to 2, I'm going to be at 4. It's really steep. Because I'm trying to look at a picture. Not everything can be solved. So you can't solve that one. We don't know how to solve it. But I can get a good picture of what it looks like. It's really a strange looking graph. Okay, what if y is negative 1? Then what's the slope here? Y equals negative 1. I don't care what x is. Negative 1, what's the slope? Negative 2. So it's steep going the other way. Whoops, wrong direction. No, I did it right. It's easy to go the wrong direction. And at negative 2, it's going to be even steeper yet, negative 4. And if I just take a point here, I'll take this point and follow the direction. It's going up like that, but look at this. I have a horizontal asymptote. What function is that? It's e to the x. If you solve this equation for y, you're going to get e to something. E to 2x, e to the x, it's the same picture. I don't even know what time we get out of here.
How do you know without solving it that there isn't like a second portion of the graph underneath?
Oh, good question. How do you know which one it is? It depends on where I start. I could start over here, and then my graph would look like this, and guess what that is? That's minus e to the x. Might be a constant. I'll put a k in there. So I don't know what it is. No. Can you choose either one? If you're just doing things in general, yes. If they give you a particular solution, and this is really important, and you probably won't remember when we get to it, but if you're given a particular solution, you're going to find out you're either going to choose this one or this one. You have to choose the one that makes the sentence true. So the initial condition goes through 0, -1, you're going to have to use this one. So it all depends. Now, try that one. That one's very interesting. Now, do you guys have my programs? Do I still have the schedule here? Oh, no, I have it. I have it on my computer. Hang on. I can get it. No, there are bells. But we'll just bring it up so I have it. And I was under the impression you were supposed to check in class. Okay. Math department information. There we go. I must have closed it out. Okay. Period 3 ends at 10:04.
That's the close time though.